Hello there and welcome back to this video series on control systems. In the previous video we have seen kind of bird's eye view of a servo motor, and we said a DC motor action we may control it either by armature control or by field control. We'll continue along the lines and try to schematic of each of these and see a bit more detail. We'll see a few aspects about armature control, field control, see their schematics and perhaps compare them and bring out a few pros and cons of each of these. Before we jump into this lesson, I would strongly urge you to go to the following link and carefully watch the content, make detailed notes, and then come back to this video. Note that all these are lowercase letters: https://bit.ly/cthum-motor. All these are lowercase letters. We saw in the earlier video that for motor to generate torque we need two things: one, current carrying conductor; two, a magnetic field cutting that conductor. The current carrying conductors are placed on the armature, which is the rotating part of the motor. So we say that armature is a rotating circuit, and magnetic field may be generated either by permanent magnets or by electromagnets. Typically these are placed on the non-moving parts of the motor, which we call stator. So these magnets are placed in the stator. We saw that if more current flows through the armature, the torque developed by the motor will be more. That is obvious. More power, more torque. More electric power drawn, more torque. So if more current flows through the armature, the torque developed by the motor will be more. Similarly, when the magnetic field is very strong, if you use very strong electromagnets or very strong permanent magnets, the torque developed by the motor will be more. This we mathematically represent as Tm, that is motor torque, is proportional to armature current. Motor torque T subscript M, that is torque generated by the motor, is proportional to the field phi. When this is true, we say that torque generated by the motor is proportional to product of phi AA, and represent this as Tm is K phi Ia, where K is the constant of proportionality. If such is the situation, we can obtain different motor torques. That is, we can achieve required torque by varying Ia, that is armature current, this Ia, and keeping phi constant. Okay, in which case we call it armature control. On the other hand, we may also achieve different motor torques by keeping Ia constant and varying this field strength. So there are two quantities here, phi and Ia. You can keep this phi constant, that is magnetic field strength constant, or you can keep Ia constant. If you keep magnetic field strength constant, you call that as armature control. If you keep armature control constant, you call it field control. We will see the schematic of what is armature control, what is field control. We see how to represent them and perhaps how to write equations for these in a subsequent video. We will draw the video step by step. This is the representation of the armature with two armature leads. Okay, this A is the symbol for armature. This is a brush. This is a brush. And then you will show armature shaft. This is the shaft on which net inertia J equivalent and net damping F equivalent sit on this shaft. The total resistance and total inductance present in the armature circuit is shown externally as resistance Ra and inductance La. When we apply a voltage EA across the armature circuit, a current IA flows through it. So this is the current carrying conductor. In actual practice, you don't see a resistor, you don't see an inductor floating in the air right next to the motor. Those are the resistance and inductance of coil inside. For convenience, we have brought them out and we are showing it. Along with this, if you have this field circuit supplied with a constant voltage, it will generate constant magnetic field as shown over here. This magnetic lines of force, they cut the current carrying conductor, and when they cut the current carrying conductor, torque is generated. When a torque is generated on a torsional system, the system undergoes a angular displacement theta m. When there is an angular displacement theta m, you will have a back EMF appearing across the armature terminals. This back EMF opposes the applied voltage EA because of Lenz's law, or one might say because of second law of thermodynamics. While all this is happening, a disturbance torque may be coming on to the motor shaft. Very similar to the way in which we drew the schematic for armature controlled DC motor, we can draw a schematic for field controlled DC motor. Okay, this shows armature, this shows resistance in the armature, and because it is field control, we keep this armature current as constant, and we show A and B as the terminals of the armature circuit. You may want to answer the question, very important question. What happened to back EMF here? We have seen back EMF in the case of armature control. What happened to that in this field control? Well, this shows the armature circuit and this shows the field circuit. IA is kept constant here and EF is varied to achieve different torques. RF is the resistance in the field circuit, LF is the inductance in the field circuit, IF is the current that is flowing in the field circuit. When a supply is given to the field circuit, you have magnetic lines, and these magnetic lines cut the conductors in the armature, and when that happens, a torque is produced. Okay, again you have this disturbing torque. We'll try to present a few points about armature control DC motor and field control DC motor. Don't get confused with AC/DC, alternate current, direct current. No, it is armature controlled DC and field controlled DC. For reasons that we see later, we can note that it is difficult to maintain the armature current constant, whereas it is relatively easy to maintain the field current constant. A second point we can notice is that the back EMF in the case of armature controlled DC motor, it acts as an inherent damping. Such a damping does not exist in the case of field controlled DC servo motor. Hence, external damping may be needed for FC DC. Field controlled DC servo motor requires greater power source, whereas armature controlled DC servo motor can be driven through amplifiers. Okay. When we actually derive the expression for time constant, we see that the time constant of FC/DC servo motor is more than that of armature control. So we say that armature control motor settles faster. Okay. Also, you can see that when you draw the functional block diagram and then mathematical block diagram, we see that there is an inherent closed loop in the AC-DC motor. It doesn't appear in field controlled DC motor. In summary, we have considered armature controlled, field controlled DC servo motor, developed their schematic diagrams, and we provided a comparison of the armature control and field control motors via schematics. Okay. We'll see a bit about armature control motor later. That's all we have for now. Have a great day.